So, hello everyone. We are here for the 12th talk in the What is series. Today we have Dhruba Sarkar from BMath second year, and he's going to speak on knot theory. He is interested in geometry in general, and so over to you.
Thank you for the introduction. And now today we'll look at the topic of knot theory. So let's start. So before we start knot theory, let's see how knot theory was first introduced. So it was first introduced by Lord Kelvin. So how did it start actually? So during the late 1800s, Lord Kelvin made it the mission of his life to categorize all kinds of atoms in the universe. So what was his idea? His idea was basically that to him, atoms were nothing but knots in luminiferous ether, which now we know that luminiferous ether doesn't exist. But back then they thought otherwise. So in 1877, P.G. Tate, he was motivated by Lord Kelvin and his works. He started the enumeration of knots based on the number of crossings. However, and here you can see these are some of the knots that he found out. However, during Tate's time, there was no formal mathematics of topology needed to study this subject. So he could not get much far with it. But towards the turn of the 20th century, with the advent of topology, works by topologists like Dehn, Alexander, and Reidemeister, it became possible to define and work rigorously on knots. So let's look at what are knots. So this is the definition. A knot is nothing but a smooth embedding of circle in R3. Here are some examples of a knot. And for some of you, a smooth embedding is nothing but an injective infinitely differentiable map. So, and this is okay. Yeah, 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 that should also be mentioned. Okay. Now, this is basically the crux of knot theory, the burning question in knot theory. How do you differentiate between two knots? So before we look at how to differentiate between two knots, we must define that when do we mean when two knots are the same? Intuitively, it makes sense when we sort of move around the strings of a knot, it should give me the other knot. But so this is the formal definition. Two knots K1 and K2 are similar if there exists a continuous mapping H from R3 cross 01 to R3, such that for all T in 01, the maps HT are homeomorphisms, and H0 is the identity map, and H1 of K1 is K2. So what it means is basically that you are morphing the 3D space in such a way that K1 transforms into K2. So here is an example. As you can see, at 1, you have a knot, and via 2, 3, 4, 5, and 6, you are changing the knot 1 to its mirror image. So this is an example. However, even though this is mathematically precise, this does not give a practical approach to identify when two knots are similar. But the next theorem, which was given by Reidemeister, this provided a breakthrough in knot theory. So how exactly? So let's look at the theorem. This is the theorem by Reidemeister. It says that two knots are equivalent if and only if one can be changed to another using finitely many Reidemeister moves. So what are these Reidemeister moves? There are three Reidemeister moves in total. The first one is called the twist, where you have some sort of arc that looks like this. You can untwist it and then twist it back again. And then the next you have poke, where you have two parallel arcs. You can poke one arc under or over the other. And then the third Ridermeister move is slide, where you have a crossing between arcs and you have a third arc under or above the crossing. You can basically move that are through the crossing underneath. So these are the Reidemeister moves, and Reidemeister proved that these are all you need to change from one knot to its corresponding equivalent knot. And now this Reidemeister's theorem, this provides a starting base to define various knot invariants on knots. And these actually help us in differentiating various kinds of knots. So this is the definition of a knot invariant. I is called a knot invariant if K1 and K2 are equivalent. This implies I of K1 and I of K2 are same or similar or isomorphic. So these knot invariants help in differentiating knots because if the invariants are different, that means the knots are definitely not equivalent. So before we look at our first knot invariant, let's define something called knot composition. So given two knots K1 and K2, we can construct another knot named K1 hash K2, which is constructed by removing arcs of the two knots and joining the corresponding ends together. For example, you can see it right here. You have these two arcs, you cut a part of these two arcs and then rejoin them like this. This is what you define as knot composition or knot sum. So, and this is also a definition of a knot, of a prime knot. A knot is called prime if it cannot be broken down further into non-trivial knots. So that means if it k equals k1 hash k2, that means either k1 or k2 is the unknot or the circle basically. So let's look at one of the first knot invariants that was discovered. It was discovered by Ralph Fox. So what does colorability mean? A knot diagram is said to be colorable if each arc can be colored using three colors, let's say red, green, and blue, such that you use at least two colors, and at any crossing, if two different colors are used, then all three colors are used. So let's look at an before that, let's see that colorability is actually an invariant. For that, you just have to check that it remains invariant under the three Reidemeister moves. Hence, by Reidemeister's theorem, it's invariant under knot equivalence, and therefore colorability is the knot invariant. So here's the first one, the first Reidemeister move, where you twist it and you untwist it back again. As you can see, the edges that go out, they remain of the same color. So colorability never changes. Here is the second Reidemeister move, and here is the third one. Hence, colorability is not invariant. So let's look at an example.
Yeah, previously.
This second randomized will increase the color, right?
Yes, but these two edges, you see, these two arcs that go away, they are not changing. Their color is not changing. So if originally this was the colorability still remains.
But just that you say a colorability, you can
Color
get
the
different
arcs.
kinds of colors
Ah,
like there's also simulation, etc. So on the left we had a knot which was colorable.
yes.
And from there we picked this move, but now we have introduced a colored heavy. So there is some choice between.
Yeah,
We
but
can just do it. Like maybe
yeah, we can do it. There is no restriction on you cannot use the green color or something.
And didn't you
So
understand the third point that in a crossing, if two colors are used, then all three colors have to appear, right? Didn't understand that. The
yes,
previous slide,
I
the
mean this is
second.
how it's defined to make it invariant in some sense.
And
Uh, we'll see a generalization of this later on. Okay.
okay.
So for example, trefoil knot, it's colorable. As you can see, this is one way we can color the trefoil knot. But the figure eight knot, however, this is not colorable. As you can see, if we color it like this, or even if you want to color it in a different way, cannot color it properly such that it satisfies all the two axioms. Therefore, we can say that the trefoil knot and the figure eight knot are different from each other, not equivalent to each other. And now you can generalize this notion of colorability in the following manner. It's called p-colorability. So a knot is called p-colorable if you can label the arcs using the integers 0, 1 till p minus 1 such that you use at least two integers, very similar to colorability. And at each crossing, this equation holds, mod p, where x is the label of the overcrossing and y and z are the labels of the undercrossings, the arcs. So, and this can also be checked that this is a valid not invariant using Reidemeister's theorem. Just check it with the three Reidemeister moves. And so this problem of p-colorability of a knot just reduces to solving a system of linear equations in ZP. If P is a prime, ZP is a field, so we can employ our usual linear algebra tools to solve it. So let's take an example for this. For example, if you have this knots and these are the labelings of the arcs, so if we write all the equations, we need to solve this uh, system of linear equations, with the exception that x1, x2, x3, x4, and x5 should be of different numbers. They all of them need not be the same. As you can see, if all of them are one, that also forms the solution, but we want to ignore that. So without loss of generality, because we are working in ZP, we can assume xn to be zero. That is, we can ignore the last column of the matrix. And in general, you can prove that this thing has rank n minus 1 in Q. Hence, we can delete any of the rows also. So, in our example, after deleting the last row and the last column, we get this. And as you can see, the matrix on the left-hand side has actually non-zero determinant in Z. So for this to have a non-trivial solution, the determinant should be 0 mod p, right? So we get this following theorem that a knot is p-colorable if and only if the determinant of the associate matrix made by deleting one row and one column of the original matrix is divisible by p. For example, if you go back, this knot, after you do this and take the determinant of this matrix, you see that this knot is 7 colorable because the determinant is 7. And it's easy to check that p colorability is invariant under Reidemeister moves. So this sort of generalizes colorability because now we can check what is the colorability of the knot. We have infinitely many choices to make. And now we can even generalize this thing. So we can generalize it using the Alexander polynomial. So what does the Alexander polynomial, how to generate the Alexander polynomial? So what do you do first is you orient the knot and label the crossings and the arcs. And now you construct the matrix such that at each crossing, it would be, so let's say you have a right-handed system at some crossing. Let's say this is your crossing L and your arc above is I. The one that passes through like this is J, and then this is K. Then what you do is at I comma Lth entry, you put 1 minus T. At J comma Lth entry, you put T. At Kth entry, you put minus 1 for the right-handed system, if the crossing is the right-handed system. Right-handed means like this. You have oriented it, right? So here it's sort of a right-handed system. And if it's a left-handed system, something like this, here you have say I, J, K, then you put 1 minus T here. Whatever is coming outside now, will you label it as T. Whatever is going inside, you label it as minus 1. And This is how you construct the matrix, and then you do the same thing. You delete one row and one column of the matrix and just take the determinant. This will give you the Alexander polynomial of the knot. This is not invariant under up to multiplication by plus or minus t to the power k for all integer k, and it is invariant under itemized moves. So this is an example, the trefoil knot that we have looked before. You can check that the Alexander polynomial is of this form, t square minus t plus 1 up to a multiplication by e to the power k. So let's look at some properties of Alexander polynomial. The first property is, it might be a bit obvious, that if you put t equals minus 1, you get back your original construction for p colorability, which is just 2 minus 1, which will give you the determinant of the knot. And this states that your Alexander polynomial is symmetric in nature. That means if you change it to t from t to t inverse, it is sort of similar up to a multiplication of e to the power k. The next property is that if you plug in t equals 1, you get plus or minus 1. And then if Rk denotes k with the reverse orientation, then also the Alexander polynomials are similar. If k bar denotes the mirror of k, then the Alexander polynomials are also similar of k and k bar. And then the last property states that for knot composition, the Alexander polynomials just get multiplied. So these are some properties. And now we'll look at Seifert's algorithm. So given a knot, one can somewhat construct a two-manifold whose boundary is a knot. However, whether or not there exists an orientable two-manifold is a question whose answer you can get using something called Seifert's algorithm. So what is Seifert's algorithm? This is the theorem that Seifert gave, that given any knot, you can always find an orientable two-manifold such that the knot is its boundary. So step one, you orient the knot, and then in the next step,
So in some
and in the next step, what you do is you break at each crossing, something like this, let's say, you sort of break it into something like this. You keep on doing this at each crossing till you are left with only oriented circles. And now for each circle, you replace it with a disk. And at each crossing where you did this, you just replace it with a twisted band. And Seifert showed that this will indeed give you an orientable two manifold and its boundary from construction can be easily seen to be the knot itself. It's fine. At each crossing, whenever we did this, we add the twisted band. And now Seifert's algorithm allows us to define something called the genus of a knot. So
How exactly we are defining the actually you can get not even consider the rectangle, right? So how do we determine like it is coming from the original orientation that we did?
yeah. It comes from the original orientation where we twist it in some sense clockwise or anti-clockwise. So Seifert's algorithm allows us to define the genus of a knot. What is the genus of a knot? It's just the minimum of the genus of all orientable surfaces whose boundary is the knot. And this is actually a very important knot invariant. And then we'll look at the following elementary but important theorem for genus of a knot. The theorem says that genus of K1 hash K2 is just G1 of K1 plus G of K2. And let me sort of give you a sketch of the proof. So for one direction, let's say you have a knot S1, which which minimizes the genus of all surfaces whose boundary is K1, and then you have a surface K2. Let's say you have something like this. Let's say this is your S1, this is your K1, this is your S2, and let's say you join K1 and K2 along these two arcs. So what you will get is something like this, with the boundary to be K1 hash K2. So this will give you one thing, that G1, G of K1 hash K2 is less than or equal to G of K1 plus G of K2. For the other direction, let's say you have this as your surface, where you minimize the genus for K1 hash K2. And let's say this was, and let's say to get back K1 and K2, you have to cut along these dotted lines. So what you do is you sort of engulf this entire K2 in a sphere in some sense. And every time where this sphere crosses S in something like this, let's say something like this, it will cross along something like this. What you do is you do something called a surgery. So what this basically means, that at each crossing, you cut the intersection, a small thick part of the intersection. So you will get your surface to have something like this, and then you join a small hemisphere, small enough so that this part remains outside the sphere and this part remains inside the sphere. After doing all this, you will get that the surface outside will be orientable and the surface inside will also be orientable, both of which have the corresponding boundary to be K1 and K2. And this will give you the other direction, and hence this gives you the theorem. And this theorem will gives us a list of important corollaries. The first one is g of k is 0 if and only if k is equal to S1. The next one is that if the genus of a knot is 1, this implies the knot is a prime. That follows from the theorem, because if you break it into two genuses, at least one of them has to be 0, which would imply one of them is nothing but a circle. And this also shows that there are infinitely many knots, because obviously you have a knot whose genus is at least 1, and you can just compose the knot with itself to get more and more knots, and the genus will keep on increasing. So there are infinitely many knots. And then this also shows that no non-trivial knot has an additive inverse. That is, you cannot just compose two knots to get back your circle or your run knot. And this also shows that every knot can be expressed as a sum of prime knots. Well, we won't see it in this talk, but it's also true that every knot can be uniquely expressed as a sum of prime knots. Um, no, I don't think it's true. I think if you take the Steve or knot, I think it does not have genus equals 1. Anyways, now let us look at something called the knot group. This is the final topic for this talk. So what is a knot group? A knot group is of a knot is defined as the fundamental group of the space R3 minus A. And this actually has an interesting algorithm to construct this fundamental group. So what you do is you orient the knot and then you label the arcs as G1, G2 until Gn. And that at each crossing you write these following group relations. Whenever it's a left-handed system, you use that. Whenever it's a right-handed system, you write this relations. And Whittinger showed that this actually gives you back the knot group of the knot. This is called the Whittinger presentation of the knot group. So let's end the talk with an example. So consider the trefoil knot. This is the trefoil knot. You label it with G1, G2, and G3, the arcs. And the Whittinger presentation of the knot group will give you this as your knot group for trefoil knot. And then with some algebraic manipulation, you can show that this is actually the braid 3 group. And that's it for the talk.
Are there any questions for the speaker? If not, maybe we can thank him again. Thank you.
References, I think there is one book by Profox, one by Livingstone, and one by Licorice. All of them are named Knot Theory.